Today we're going to talk about linear combinations and systems of linear equations. But to do this, let's quickly review some ideas of subspaces. Assume that V, along with a vector addition plus and a scalar multiplication dot, is a vector space over field F. Recall that the following two statements are equivalent for a subset W of V. First, the triple, the set W, vector addition plus, and scalar multiplication dot, form a vector space over F. Second, the following three conditions hold for the operation vector addition plus and scalar multiplication dot, both defined on V. That is, the zero element, capital O, is in W. There's closure under vector addition for W, meaning if X and Y are in W, then X plus Y is in W. And third, there is closure under scalar multiplication for W, meaning given a number C in our field F and another vector X, then C times X is in W. Any subset W of V satisfying either of these equivalent statements above is called a subspace of V. Remember that this is just a concatenation for saying a subspace is a subset that is also a vector space. Last time we started to write down some examples of such spaces. Let's let V be a vector space over F. Then we can either let W equal to the whole vector space V, or we can let W just be the set that consists of one element, namely the zero element from our vector space. These are both examples of subspaces of V. As another set of examples, let's consider the M tuples over F. That is, we'll consider an array where here we have coordinates x1, x2, so on and so forth through xm, where each coordinate x sub I is in our field F. This here, recall, is a vector space over F if we use the usual vector addition and scalar multiplication. Fix a point that we'll call N in this space V, and consider the following so-called hyperplane going through the origin. That is, this here will be the set of vectors x1, x2, so on through xm in our vector space V, satisfying the condition that a1 times x1 plus a2 times x2 plus so on plus am xm equals 0, where here the a sub i's just form the coordinates of our given point N. Then this W is another example of a subspace of V. We found before, in a very special case when our field F is the real numbers and our M is equal to 2, that we have a nice geometric interpretation. In this case, our hyperplane is nothing more than a line through the origin. And in fact, the previous result asserts that given the real plane R2, any line through the origin is an example of a subspace. But are there other examples of subspaces? Today we'll discuss this and more. Let's consider three space. That is, we'll simply draw pictures now in 3 dimensions. And here we'll choose 3 vectors that we'll denote by capital A, capital B, and capital C. You can see from the diagram here that we could choose capital A to be the blue vector, denoted by I in the diagram. We could choose B to be the red vector, denoted by J in this diagram, and we could choose C to be the green vector, denoted by K here in the diagram. What we'd like to do is define a plane going through these 3 points. Here you can see in the diagram, we've actually replaced the uppercase letters with lowercase letters, but still the lightly shaded blue region is the region that we're calling W. We'd like to know how to write such a W down. Well, one way we could do this is define 2 new vectors, U, which would be B minus A, and V, which will be C minus A. You can think of these as vectors that start at the point A and they end at B, or they start at the point A and they end at C. This will correspond to the edges of the triangle that you see in the diagram. The idea here is that if we want to have a plane, then we'll have it going by starting at the point A And we can move now in two directions along this plane, either in the u direction or in the v direction. This is what we mean by our plane going through these 3 points. We can consider the set of vectors x such that x starts at a vector a, and now we can move in any of the two directions u and v. So x should be a plus a scalar times u plus another scalar times v. Now if we simply substitute back in what we had for u and v, then we see that w is also the set of x such that we have now Ra plus Sb plus Tc, where R, S, and T are real numbers such that their sum is equal to 1. We won't be so interested in the latter definition in terms of R, S, and T. We'll be much more interested in the first one, only involving S and T as well as U and V. But try to keep this picture in mind when we write down this set W. The proposition now says that this W will be a vector space if we can pick A to be the origin. That is, our W, which is now a plane going through the origin, is an example of a vector space. Let's quickly explain why this is the case. Remember that to show that a certain set is a vector space, we really want to show that this is a subspace of what we were calling capital V, that is 3 space. So we have to verify the 3 axioms hold true. First, we'll check that there is a 0 element in the set W. Well, we can write 0 as the linear combination 0 times u plus 0 times v. That is, here we simply scale the vector u by this real number 0, and we can scale the vector v by this real number 0. So once we do that, then of course we're simply left at the origin, namely capital 0. Next, let's check that we have closure under vector addition. Let's pick 2 points in our plane, x and y. What this means is x looks like s1u plus t1v for some real numbers s1 and t1. Similarly, y is s2u plus t2v, where s2 and t2 are 2 real numbers. If we add x and y, we can express this as s times u plus t times v, where s is just the sum of s1 and s2, and t is the sum of t1 and t2. These are just other real numbers. Therefore, x plus y is in the same form as our definition for w, so we see that x plus y is also an element of w. We'll let you check here that a very similar argument holds if you want to check that w is also closed under scalar multiplication. It's pretty much the same idea. So let's think about geometrically, how does this look? Here we want to consider our w, and remember that our capital A is the origin. So our w now simplifies to be in the following form. It's the set of vectors x in 3 space, so x looks like s times u plus t times v, where s and t are real numbers. As we said before, this is nothing more than a plane through the origin. Here you can see 3 different examples of planes through the origin. The red plane, the one that's going through the xy plane, that's an example of a w. The blue plane, this is going through the xy plane, this is another example of w. And the green plane, this is going through the yz plane, this is yet another example of w. Here you can convince yourself that there must be infinitely many examples of w. That is, infinitely many examples of subspaces of 3 space. Now let's try to combine all of this together with what we saw even in the last lesson. Let's go back to the example where v is R2, that is the real plane. We've already seen that every line through the origin gives an example of a subspace of the real plane. Well, we found before that our w, our line through the origin, we can express as the set of vectors satisfying a certain equation, a times x plus b times y equals 0. Now, if we were to solve for y in terms of x, then what we could actually see is that x looks like a scalar multiple times negative b, and y looks like a scalar multiple times a. In other words, every vector on the line, x comma y, looks like a scalar multiple times this vector negative b comma a. So we can either write the equation of our line, ax plus by equals 0, in terms of saying that we have a scalar multiple of just one vector. Geometrically, this just says that if we have a line, then this only goes in one direction, either infinitely far in one direction or infinitely far in its opposite direction. That's the idea of saying that it's a scalar times a vector. But what about the example that we just worked out? Let's consider now V to be R3, namely 3 space. As we've just worked out, every plane through the origin is a subspace of V. Well, you may recall that one way you can express the equation of a plane is by saying that it's the set of vectors x, y, z in 3 space, so that ax plus by plus cz equals 0. Just like before, we could try to solve for maybe z in terms of x and y, and what we find is that all of our points x, y, z look like a scalar times u plus another scalar times v. What we're saying here now is that if we're in the plane, we can move infinitely far in 2 different directions, either in the u direction or in the v direction. But wait, is there a general pattern here? If we try to say something to the effect of a sum of variables equals 0, can we always write this as maybe scalars times vectors? So let's try to write down a slightly more general definition to get a better idea of what should happen. Let's let our vector space, namely a non-empty set V, vector addition plus, and scalar multiplication dot, be given. We'd like to choose a finite subset that we'll denote by capital S. In this case, we will list the vectors as u1, u2, through u sub n. Now, given any scalars, that is numbers a1, a2, through a sub n, we'll call a vector v a linear combination of vectors from S if we can express v as a sub 1 times the vector u sub 1 plus a sub 2 times the vector u sub 2 plus so on plus a sub n times the vector u sub n. We'll call the numbers a sub I coefficients in this linear combination. The big result says that if we take such linear combinations and put them all together into one set, then this set is a subspace of V. We'll give some definitions here. Recall that S is given, and then we can express this W in terms of S. We will say that W is the span of S, or equivalently that S generates W. In the special case where S is the empty set, that is, S has no elements, we simply define the span of S as the trivial subspace. That is, the span of S is, by definition, the singleton set that consists of just the 0 element. Let's try to sketch over why this proposition is true. We're essentially going to use ideas that we've already seen. Remember that we have to verify that 3 axioms hold true in order to show that W is a subspace. Well, first, we need to verify that the 0 element is in W. This follows exactly in the same way from before. If I take the number 0 times any vector u sub 1, I simply get back the 0 element. Now, if I add the 0 element to itself any number of times that I want, I get back the 0 element again. So we can always express the 0 element as a linear combination of elements from S. Next, let's check closure under vector addition. Well, let's say that x and y are 2 vectors in W. Remember, this means that x is a linear combination that I can write in terms of coefficients a sub i's, and y, similarly, will be a linear combination in terms of the coefficients b sub I. Now, if we add these 2 together, then we can see that x plus y is a linear combination in terms of these coefficients c sub I, which equal to a sub I plus b sub I. Hence, the sum x plus y is also in our set W. A very similar argument holds when we consider closure under scalar multiplication. So this does indeed show that W is a subspace of V. So in particular, this gives us a way to write down lots and lots of examples of subspaces. Let's try to recap by reviewing some examples that we've already seen. Let's go back to the case where we're dealing with the real plane, namely V is equal to R2. As before, we've seen that every line through the origin is a subspace of V. And we could also write our line as the collection of points xy that look like they are scalar multiples of some vector u. In this case, our line W is the span of S, where S is the singleton set that just consists of this one vector. Morally, what we're saying here is that the line really only moves in one direction. U is the vector that determines that direction. Let's now consider the case where V is R3, namely we're dealing with 3 space. We've also seen that every plane through the origin is a subspace of V, and in fact we've written things so that the set of points on our plane through the origin correspond to linear combinations of 2 vectors U and V. In this case, we'll say that W is the span of S, where S consists of these 2 directions U and V. Now, I'd like to end the lesson by discussing why should we care about all of these fancy definitions? How is this going to help us in a class that discusses linear algebra? So we'll finish today's lesson by discussing why the concept of linear span is indeed a useful one. In general, let's say that we have a system of m equations and n unknowns. We've written things here so that the coefficients a sub I are numbers that are given, and on the right-hand side, again, we have coefficients b sub j that are given. It's the variables x1, x2, ... through x sub n that we'd like to solve for. Now, in this class, we're going to try to express this system as a product of matrices. Recall that a matrix is nothing more than an array that has m rows and n columns. So eventually we're going to discuss what does it mean to be a matrix product, and we'll try to define the equation A times X equals B. What we're going to find is that if A is invertible, in some sense, we can divide by A and solve for X. However, most of the time in linear algebra, A is not invertible. This is why we will eventually perform what's called Gauss-Jordan elimination. But here we're getting slightly ahead of ourselves. Let's go back to our equation and let's simply ask one question. When will this system have at least one solution? When can we find at least one collection of x1, x2, and so forth through x sub n, such that this system of m equations and n unknowns does have at least one solution? What I'd like to do is rewrite this in terms of a linear combination of vectors. Here now we're going to express the equations above as a sum that's just expressed in terms of one equation. If you stare at the left-hand side and now multiply the scalar x1 times the vector x11, x21, ... through x sub m1, and if we add these all together, then really on the left-hand side we find nothing more than the equations on the left-hand side at the very top of the slide. So writing things here at the bottom of the slide gives a nice shorthand way of expressing this long system of equations at the top. We're going to try to view this set of equations in terms of a finite set S, where this S here simply consists of the coefficients a11, a12, so on and so forth, coming from this system of equations. So again, our system of equations now can be written in terms of just one equation, but involving vectors. The statement is, if we're given such a system of m equations and n unknowns, then there is a solution, x, which of course is a vector consisting of these n coordinates, x1, x2, through xn, the system has a solution if and only if the right-hand side vector b is contained in the span of the columns S. We're going to use this result over and over again. In fact, we're actually going to prove this rigorously as the course goes on. Thanks for listening.